So today we have a Damian that is a PhD student at BITS University. So yes, you can start now, Damian. Damian, if you are ready.
Okay, cool. I'm just going to share my screen. Can everyone see my screen?
Yes, we can.
Okay, cool. Okay. Okay, can everyone hear me as well?
Yes, we can.
Okay, cool. Good afternoon to everyone. My name is Damian, and I'm currently a second-year PhD student working with Matt Hilton and Unikrishnan Sureshkumar at Wits University in Johannesburg. And today I'd like to share more about my research on the stellar mass distributions in galaxy clusters. Hence, my talk is entitled Cosmic Chronicles, Tracing Stellar Mass Growth in Galaxy Clusters from ACT DR5. So just a brief outline of my talk. I'll provide an introduction to the stellar mass function and Schechter function. I'll discuss some of the properties of the cluster stellar mass function. I'll introduce the data and the methods we have used. Then I'll present some of our preliminary results and analysis, discuss our next steps, and finally present our summary and conclusion. So an important observable of galaxy populations is a stellar mass function, or SMF, which basically describes the number density of galaxies as a function of stellar mass. In the context of galaxy clusters, the SMF is, galaxy clusters are massively gravitationally bound systems. The SMF becomes particularly important as it provides crucial information about the distribution of stellar masses within clusters and the mechanisms that lead to this observed distribution. Deriving SMFs in clusters is generally a simple task, since clusters provide a rich collection of galaxies all at the same distance, and the density is high enough to identify members photometrically. So accurate measurements of the cluster SMF can help us understand the impact of the cluster environment on galaxy formation and evolution. So here's an image of one of the largest galaxy clusters ever discovered, commonly known as El Gordo, which is Spanish for the fat one. And it was discovered by the Atacama Cosmology Telescope using images taken from ESO's Very Large Telescope and the SOAR telescope combined with X-ray imaging from Chandra. So analogous to the luminosity function, the overall signature of the SMF reveals that after an exponential rise, the SMF turns off at a characteristic stellar mass, m star, which is called a knee of the function, and then follows a power loss at lower stellar masses known as the low mass slope, or alpha. Now, the most popular fit to the SMF is the Schechter function, which was proposed by Schechter in 1976, which is given by the following equation, where phi star is a normalization parameter, m star is a characteristic stellar mass, and alpha is the low mass slope. So this slope is generally decreasing for alpha greater than -1. Flat for alpha equal to -1, and increasing for alpha less than -1. So alpha is typically negative, implying a large number of galaxies with low stellar masses. And the Schechter function usually it describes reasonably well the observed SMF, but mismatches do occur at the high mass end due to the presence of usually massive galaxies. So the cluster SMF is typically dominated by two galaxy populations, where the high mass end is characterized by bright early type or red galaxies that follow a Gaussian-like stellar mass distribution, and the low mass end, which is characterized by star-forming blue galaxies that follow a steep power law-like function. The presence of brightest cluster galaxies, or BCGs, which are typically giant elliptical galaxies located near cluster centers, are often the likely contributors to spikes in stellar mass that we observe at the high mass end of cluster SMFs. So as such, it's common practice to exclude these sources by implementing a radial cut or something around the cluster core. Alternatively, as we see here in this figure, a Gaussian function can be used to model the high mass end. So this figure is taken from study from Wen and Han and his voluminosity functions, but the principle is the same. So this essentially means fitting a Schechter function to the low mass end plus a Gaussian to the high mass end. So the main aim of our study is to examine the stellar mass growth in a large sample of galaxy clusters by measuring their composite stellar mass functions from redshift of 0.2 to 0.8. Now for a cluster sample, we make use of the large cluster catalog presented in the fifth data release of the Atacama Cosmology Telescope, or ACT DR5. ACT was a 6-meter millimeter wave telescope located on Cerro Toco in the Atacama Desert in Chile. And it was optimized for measuring angular power spectra and clusters via the thermal Sunyaev-Zel'dovich effect, or TSZ for short. The Sunyaev-Zel'dovich effect causes a change in apparent brightness of the cosmic microwave background radiation towards a cluster of galaxies or any other reservoir of hot plasma, essentially. And the essence brightness of clusters basically depends largely on mass and not on their redshift. So basically, this allows for the construction of mass-limited samples, essentially. The DR5 catalog in particular, presented by Hilton et al. 2021, consists of 4,195 massive galaxy clusters drawn from a survey covering roughly 1/3 of the sky and selected via the SZ effect. So this catalog is one of the largest SZ selected cluster samples assembled to date, spanning the range of 0.04 to redshift of 1.91, consisting of 222 clusters with redshift greater than 1, 868 newly discovered systems, and all within a sky coverage of 13,211 degrees squared. And from this catalog, we selected a total of 1,663 clusters that had a signal-to-noise ratio greater than equal to 5 in the redshift range of 0.2 to 0.8. So here's just, we have the DR5 cluster search area shaded in gray. This is overlaid on a Planck 353 gigahertz map. And you can see the survey has a large overlap with some other deep optical weak lensing surveys, such as DES Dark Energy Survey, which is in blue, HSC, which is magenta, and KIDS, which is in green. So in order to examine the cluster sample, we make use of the optical data from the 10th data release of the Dark Energy Camera Legacy Survey, or DECaLS DR10. And DECaLS makes use of one of the dark energy camera, or DCAM. And DCAM is basically located on a Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory, I think, or CTIO. And the large field of view and sensitivity of DCAM makes DECaLS an efficient way, a good option for obtaining photometry in the GR and Z optical bands. So DR10 includes objects from DECaLS in newly observed regions of the sky, and also new I-band data covering a sky area of approximately 15,300 degrees squared with 6 optical bands, GRIZ, W1, W2. Those are the WISE bands. So here are the footprints of the optical imaging surveys contributing to DESI imaging. The region covered by the other two DESI legacy surveys, BAS and MZLS, is almost entirely in the North Galactic Cap, while DECaLS covers the entire South region. And the legacy surveys essentially just provide deeper imaging, and I think they can leverage existing spectroscopy in these regions, unlike most other existing or ongoing deep imaging surveys. So taking advantage of the accurate photometry from DECaLS 010, we use photometric redshifts or photoz's to construct redshift and cluster mass-binned composite cluster SMFs over the stellar mass range of 10 to the 10 to 10 to the 12.5 solar masses. So we use log scaling to this. So due to a large cluster sample, we were also able to bin clusters into narrow redshift bins of width 0.05 over this large redshift range. And cluster membership was determined probabilistically using the galaxy photo redshift probability distributions. So in order to select cluster members, we first chose galaxies within the approximate cluster virial radius, which is R200M. And this is the radius within which the average density of the cluster is 200 times the mean matter density of the universe. Secondly, we only selected galaxies found within a redshift slice of 0.05 of the cluster redshift. And these were essentially what we selected as our cluster members. Our stellar masses were estimated using an SCD fitting method and a popular stellar population model from Burgel and Charlot, which is commonly known as BC03. And that uses a Chabrier IMF as well, a Chabrier initial mass function. So a common issue that also arises in LF and SMF studies is usually incompleteness at the faint end or low mass end of the stellar mass function. And this is because as we move to higher redshift, we tend to see a falling off in the number of faint or low mass galaxies due to optical survey limits or depths. And to correct for this, the stellar mass limit can be drawn from a volume limited sample, which is what I've shown here in the optical survey. And in our case, we got a stellar mass limit of 10 to the 10 solar masses from a few volume limited samples in DECaLS DR10. And from this limit, we then only select the cluster galaxies above this limit. As mentioned earlier, high mass galaxies or massive galaxies, particularly BCGs, tend to have an impact on the shape of the SMF. And this obviously influences the Schechter model parameters M star and alpha. And to combat this, we decide to exclude the highest stellar mass per cluster, which is most likely the BCG. So following a popular method by Coles 1989, cluster galaxies that satisfied all of the previously mentioned above conditions were counted into stellar mass bins for each cluster in each respective redshift bin. And that basically gives us a composite stellar mass function. And this is given by this first equation, and where the composite SMF for the redshift bin denoted by n subscript Cj is given by the sum of the individual cluster SMFs denoted by n subscript ij, that's weighted by a normalization or optical richness for each cluster, represented by n subscript I0. And this composite SMF is then further weighted by the number of contributing clusters to the redshift bin, denoted by m subscript j, and by the sum of all the cluster normalizations given by n subscript C0, which is also given in this equation here. So the errors in the total composite SMF is given by the last equation, where delta n subscript ij is the error, which is the error on the individual cluster SMF, is determined by Poisson statistics, and the weightings are the same as the composite SMF. We also bin clusters by cluster mass. So not to be confused with stellar mass, but by cluster mass, by choosing the top and bottom 25% of clusters ranked by their mass. So this essentially creates like a low cluster mass and a high cluster mass subset for each redshift bin. And once this was done, we repeated this process for each redshift bin And this essentially gives us a total of 12 composite stellar mass functions, 12 low cluster mass subset stellar mass functions, and 12 high cluster mass stellar mass functions as well. So once this was done, a single Schechter function was then used to model our 12 redshift-binned composite SMFs and our subset SMFs as well. Monte Carlo Markov chains, or MCMC, were used to estimate the best fit parameters, M star and alpha, from the Schechter function. An analysis and results shows that a single Schechter function describes the SMS reasonably well, since the uncertainties in the Schechter parameters are low, despite the deviation in stellar mass at the high mass end. Both of the cluster mass subsets appear to follow similar trends in stellar mass, and their Schechter parameters are within 3 sigma of the total cluster-binned sample parameters. So this agreement that we see in each redshift-binned implies that the evolution of these two parameters, M star and alpha, are essentially independent of cluster mass in this case. So looking at the time evolution of the characteristic stellar mass and low mass slope, we observe that these parameters are well constrained with redshift. A clear and obvious trend is observed in the mid-redshift bands. I think that's pretty obvious in both plots, from redshift of 0.4 to 0.6, where M star is seen to have a slight decrease or dip, while alpha becomes less negative or shallower or flatter. Usually a shallower slope and a high M star value indicate a dominance of high mass or passive galaxies in the SMF. However, here we observe decreased values of M star, but we are still seeing flatter values of alpha. So clearly, whatever is driving the trend in M star is driving the trend in alpha. So this points to some degeneracy that obviously M star and alpha are dependent on one another. We've also compared our values to some field studies denoted by F and cluster studies denoted by C, but we do need further analysis to determine degeneracy in M star and alpha and find out the cause of what's driving these trends, hence why these results are preliminary right now. So despite excluding the highest stellar mass per cluster, we have still noticed that there's an excess in stellar mass at the high mass end, particularly in the mid-redshift bands in our range. And to combat this, we decided to model a combined Schechter plus Gaussian fit. So as seen before in the Wen and Han figure I showed, this combined model is a big improvement on a single Schechter fit. As seen here, the Schechter function, which is shown as this green or dashed green line, seems to model the low mass end pretty well, while the Gaussian function, which is represented as a dashed dot orange line, models the high mass end pretty well and accounts for this excess in stellar mass. So this combination of these two models is then what we get, this combined solid black line. That's our combined model fit, and it fits pretty well as well. So finally, we also look to track the stellar mass growth in clusters with time. So to do this, we measured the fraction of total cluster stellar mass to total cluster mass, and this gave us a fraction, and then we summed this fraction for all clusters in a particular redshift band and took the average of that fraction and converted it to a percentage. And we've also done this for the cluster mass subsets as well. And here we see that these fractions with redshift together with their uncertainties and 1 sigma scatter, we obviously see a clear trend of decreasing fractions towards higher redshift, which obviously implies that cluster stellar mass has grown from redshift of 0.8 to 0.2. So obviously these clusters are assembling more stellar mass as they are growing. And in this case, for the total sample, that factor of growth is a factor of 3, So from a factor of 3 growth from redshift of 0.8 to 0.2 for the total cluster sample. And then for each subset, it's a growth factor of 3.5. But we can see that for the low cluster mass sample, they have a higher, appear to have slightly higher fractions for low mass clusters at low redshift. So yeah, I mean, basically indicating that these clusters have a much higher percentage of stellar mass within them. So what's next for this work? Well, the next step is hopefully publication, where we still need to perform further analysis to figure out what's driving the evolutionary trends that we see for M-star and alpha. We would also like to compare results with more literature and more simulations. Even the stellar mass fractions, we'd like to compare them with some simulations, maybe from LSST and G possibly. We hope to implement our methods on the yet to be released ACT DR6 cluster sample using deep photometry provided by the Vera C Rubin Observatory, which is currently under construction, but expecting first light in 2025. So the 8.4 meter Sunyaev survey telescope at Rubin is equipped with this camera, which is the largest digital camera ever built, LSST cam. And this will take detailed images of the southern hemisphere for the next 10 years and study millions of galaxies with incredible detail. So it's pretty exciting. And this is Rubin's observatory. So in conclusion, the cluster SMF basically provides us important information about the distribution of stellar masses within clusters and the impact of the cluster environment on galaxy formation and evolution. We have made early measurements of the composite cluster SMFs for 1,663 ACT DR5 clusters, binned by both redshift and cluster mass using deep photometry from DECaLS 010. We observed that while a single Schechter function provides a good description for SMFs, a combined Schechter and Gaussian model helps us to better account for the excess in stellar mass at the high mass end. Cluster mass subsets SMFs are consistent with the total SMF, which suggests that the evolution of M-star and alpha is independent of cluster mass. The decreasing trend observed in cluster stellar mass fractions suggests that cluster stellar mass has grown by a factor of 3 from redshift of 0.8 to 0.2 for the total cluster sample. We still require further analysis to figure out the trends in M-star and alpha, and finally implementing our methods on the ACT DR6 sample, which is yet to be released using deep photometry from LSST is a logical way forward for this work. So that's it. Thank you.
Thanks, Damian, for your talk. So maybe we can move to questions from the participants. So, Jinje.
Hello. Yes. Hello. Am I audible?
Yes.
Yes, can hear you.
Okay, good. So yeah, I generally I have a question. Actually, it's a very basic question. I know this way of finding the clusters and so on, and Matt Hilton, etc., and also a lot of other people have found a lot of clusters using SZ, but because your SZ is kind of more. I mean, you would be to see a good SZ signal, you would need a very good CMB maps and like ACT and so on. So then that tends to be seeing more massive clusters. So I mean, I have no doubt this will find clusters, but I worry for its efficiency. Perhaps the optical telescope and so on would be much better in terms of finding all big clusters or small clusters in the universe.
No, that does make sense. Yeah, I think a follow-up with optical is always good. But it just the main benefit of SZ is just that it allows us to just get the really massive clusters. So if you're doing science with looking at really large the massive clusters particularly, it's helpful in that case. but yeah, I mean, so the DR6 release that is coming up. I'm not really sure how the maps are looking for those, but there could be an improvement in the maps they're using. But I'm not entirely sure on that. Yeah.
Yeah. I just one extension comment, extended comments is that I think the attraction for me to use DR6 results, the ACT DR6 results.
Yeah.
By the way, they have released the SZ and lensing map, but they haven't released the CMB map yet.
Yeah.
I guess
that's-
they will release. I'm looking at their webpage almost every few weeks to just
Yeah.
double check when the data will be uploaded. So I mean the attraction to me is that you can get pretty good SZ measurement to see those in order to find those low mass clusters or even filaments, because
Yeah.
that's where the cutting edge of missing baron and such weak signal is at, instead of the big ones. Big ones, of course, they are bright, etc. It's relatively easier to see. But for me, the the more challenging goal is to find missing barons associated with these low mass clusters or even filaments. Yeah.
Yeah. I mean, there's also like I think I read this one. I think it's a recent paper by Wen and Han, and their sample of clusters was a massive range, and that was in optical. So they had like thousands, 20 of thousands of clusters in their sample, and that was in optical. So yeah, I think it's just the science that you're actually gonna be using. It depends on your science. It's your science goals with the cluster sample. It depends, I guess.
Yeah. Okay.
Yeah.
Okay, more questions. Vanelli?
Thank you so much for the nice presentation. So I have a question there. How might these findings impact our understanding of the galaxy formation and evolution within the cluster?
Sorry, can you repeat that?
I'm asking that, like, how might these findings impact our understanding of a galaxy formation and evolution within the cluster?
Okay. Yeah. So the main takeaways to look at is, well, for example, we look at the cluster stellar mass fractions. We are seeing, how these clusters are evolving in terms of their stellar mass and their mass accretion from redshift of 0.8 to 0.2. So because we are looking at like we're looking at the fraction of stellar mass compared to total cluster mass. These stellar mass fractions are basically helping us to get a picture of how these clusters are evolving, whether there's a dependence on cluster mass. Are more massive galaxy clusters accreting stellar mass faster compared to low mass clusters. And then when you look at even with the Schechter parameters, these help us to constrain how stellar mass is distributed in clusters in each redshift range or redshift bands. So from 0.2 to 0.8 redshift, I think for most people isn't a significant chunk of cosmic time, but I mean, you're looking over the past, I could be wrong on this, but past 9 billion years. So yeah, we still, as I said, we still need to gain more perspective to understand what's driving the evolution of these parameters, as M star alpha parameters, because for example, if I take the mass slope alpha, that basically tells us if there's a higher abundance of low mass galaxies in the cluster SMF, or it basically helps us to track how that distribution is moving with time. And if you look at this trend, what it's saying is that in this mid redshift range, in the higher end of our redshift range, we are seeing that there's actually a higher abundance of high mass galaxies. And normally, as you move to higher redshift, you typically should see that there are more low mass galaxies at higher redshift. So yeah, we still need to figure out what's actually driving these trends, and if it's something to do with the stellar mass limits, if it's something to do with our method. Yeah.
Okay. Thank you so much.
Okay, more questions. So, okay, what I will think, just a comment, a question. What I will think about this, your results, is about thinking what is calling to the down sounding scenario of
Yes,
a
yes.
galaxy formation. That is basically that the low mass objects as AGN and clusters evolve first than their high mass counterparts, a high redshift, basically. So
Yeah,
to
no, that's
see,
correct. Yes, yes. Cosmic
so,
downsizing is a possible explanation. Yes, I agree. Yeah.
so looking into that to interpret your results, so is a good idea. And I don't know if you have more questions from Gingy or somebody else. Otherwise, yes, we can say thanks again to Damian. And I would like to advertise the upcoming seminar next Friday. I still have to send the email by John Paul that will be visiting us from Switzerland. So he will be here on UKCNM, but we will try to stream it by Zoom as well. So you are all invited to participate. So thanks again, Damian, and see you next week.